Hello everyone. Today I continue to repair this old-time radio. In the first and the second parts of the videos, I spoke in Vietnamese. Today I try to speak in English, and I hope more people can understand the video. This is the JVC radio made in Japan around 1960s. Even though this is the transistor solid-state radio, it still have a look of a tube radio. As you can see here, the metal frame and the big components are mounted on the terminals like this. You can find in a tube radio a big variable capacitor of tuner circuits. And you see the metal plates moving as the capacitor changes value. The potentiometer and the on-off switch is in the same unit. And you see underneath the PC board and the cable and wire jumping from place to place. The problem of this radio is no audio for both AM and FM bands. This is the partial schematic I drew back from the radio.
Audio amplifier circuit. Speaker 8 ohms, 1.6 watts. FM detection circuit or FM detector. AM detection circuit or AM detector. The output from FM detector comes out on this line, and the AM come out from this line. The band select switch selects either FM audio or AM audio to pass to the audio amplifier circuits. The potentiometer controls the volume of the radio. And I checked section by section, and up to the point I found out this transistor is bad. I removed it out and tested and confirmed this transistor is bad. I already bought a new one and placed it on board. The radio is now alive, and I can hear very clear sound for both FM and AM band. Now I try to explain some more about the AM and FM detection circuits. When the band select switch to the AM band, the AM intermediate frequency 455 kHz appears on the primary coil of the black transformer here. Assume the signal at point A look like this. This is the 455 kHz sine wave, and the amplitude of the sine wave is modulated by the audio signal. This signal transfers through the black transformer as seen at point B. Look like this. And it's very much the same like this one. The small signal diode is in reverse. It will chop up the top part of the signal. And with this connection, only allow the current flow from this way, and allow only the negative part of the signal as seen at the point C. The RC low pass filter remove the high frequency of this signal and yielding the audio output at point D. And this point D is go here and go to the amplifier circuit and go to speaker. To see the AM operation, I have a signal generator to generate AM IF signal. And the output of the signal generator connect to the channel 1 of the scope, as you see here on the yellow waveform. This is the 455 kHz sine wave, and this is modulated by 1 kHz at the envelope of the sine wave. And that signal I inject into at this point here. And this is the pin B of this transistor, and this transistor is shared for both FM and AM IF amplifier circuits. And this signal here is amplifier and go through connection of the coil and go to the black transformer here. I'm going to probe at point B and point C. At point C, we have two waveforms to see, one without the capacitor and one with the capacitor. So right now I'm going to probe at point B for the channel 2. So that's the signal at point B, and now I'm probe at point C. So you see the top part of the signal is chopped up and only a negative part, and this one have an envelope of 1 kHz sine wave, and it still have the high frequency component inside here. And now I install the capacitor of the RC low pass filter, and you will see the high frequency will be removed. Now I connect the capacitor back to the circuit. And so you see this one is the audio 1 kHz sine wave here. I'm going to turn on the volume, and you probably will hear the 1 kHz at the speaker. And now I going to explain about the FM detection circuit. For the untuned transformer, we have the Vout and Vin is in the same phase. For the tuned transformer, the output of the transformer based on these two characteristics and represented by two of this waveform here. This is the frequency domain for both amplitude and phase. At the resonant frequency, the magnitude of the Vout is maximum, you see. And for the frequency above or below the resonant frequency, the amplitude is get decreased on both sides. And for the variation of the frequency, it not only changes the amplitude of the Vout, but also changes the phase of the Vout. And you see here, when the frequency at the resonant frequency, we have the 0 degree phase, so that means the Vout and Vin are in phase, 0 phase difference. But when the frequency input is above the resonant frequency, we see the phase positive. The phase positive, that means the Vout leads Vin. And you can see here on the drawing here, at the frequency of resonant frequency, we see the Vout and Vin is in the same phase. But when the frequency is greater than the resonant frequency, you see the Vout leads Vin. That means you see the red waveform is go in front of the Vout go in front here. And for the frequency below the resonant frequency, you see the Vout lags Vin, so you see go behind Vin. The FM detection circuit in this radio employ the variation of the phase when the frequency changing to detect or to convert the FM intermediate frequency to the audio signal. So it's based on the variation here. So you see when the frequency changing, and you see the phase of the output is changing, and actually you can see this, the red signal here is when the audio changing the frequency, and you probably see the red signal is go back and forth from compared to the Vin. Yeah, this is to draw back the FM detector circuit here for simple to look. And the FM detector include the pink transformer, which is untuned transformer, and this is tuned transformer, blue color. The pink transformer is wired up in such a way it's always 90 degrees away from the primary coil here. This coil and this coil hit the same phase, and this coil here, VP is 90 degrees different phase from the pink, but this is the untuned transformer, and this here is the tuned transformer. The output of the transformer will be variation with the frequency on the primary coils over here. You see this the IF, FMIF coming here, and the pink transformer, because it's unchanged with the frequency, it is used for the reference point. It's used for the reference signal. So this waveform here try to explain how the FM detection circuit works. You see here, when the frequency is equal to the resonant frequency, you see this is the V1 and this is V2. So V1 is this point, the signal V1, here the signal V2. The V1 and V2 are 180 degrees apart. So we see here V1 and V2 is kind of opposite. That means 180 degrees different. And we have VP here. And the VP is 90 degrees away from the V1 and V2. And you see here the VP from the pink transformer connect to the middle tap of the blue transformer, and V1 here and V2 here. This waveform is drawn from the frequency equal to the resonant frequency. You look at here, the diode V1 is conducted when the V1 is positive relative to the VP. And over here, we have the V1 is the red one, and VP is the purple line here. And the D1 is only conduct when the V1 is positive relative to the VP. So you see the shade here is the time the diode D1 is conducted. And the diode D2 is conducted when the VP is positive relative to the V2. And you see here that the VP is positive of the V2. You see the shade section here is the time the V2 conduct. And at the resonant frequency, you will see the time amount of conduct of the D1 and D2 is about the same. And the current flow to the D1 and D2 is the same. That yielding the voltage potential between this point and this point is about the same. So we have the V in over here around 17 volts. You probably see here. And you see voltage at this point and this point is about 17 volts. That is the case when the frequency is at the resonant frequency. And when the frequency is higher than the resonant frequency, you see the voltage at V1 and V2 shift, but the VP is constant. It's not changing the phase. But this one is changing the phase. So you see here, the voltage V1 and V2 is shift to the left. Diode D1 is conduct when the V1 is positive compared to the VP. That means you see this shake part over here and this shake over here. For the D2, the current conduct when the VP is positive relative to the V2, VP positive. So this shaking part over here, we can tell the diode D1 is conduct more than the D2 conduct current. And that yielding the voltage at this point is increased, and it's higher than the voltage at this point. The middle tap here is the voltage is raised up at this point. When the frequency is below the resonant frequency, V1 and V2 shift to the right, and the VP is still constant. This section here is the amount of current that the D1 conducts here, and this section here is amount of current that the D2 conducts. And you see here, there's more current passed to the D2 than the D1, and that's bring the voltage at this middle point is decreased voltage here. So in summary, so we have when the frequency is at resonance frequency, the voltage at this point and this point is about the same. And when the frequency increases, the voltage at this point is higher than this point, make the voltage at midpoint increase. And when the frequency below the resonant frequency, voltage at this point is higher than at this point, and we see the voltage decrease. And that voltage is connected to the audio amplifier. So we have the signal of variation of the frequency coming. We have the signal of the amplitude variation coming out here. So that the FM circuit detector works. And back to the detailed circuit diagram here, and you see the pink and the blue transformer. Here I have the signal generator generate FM modulation signal, and that modulation signal is injected into this port here, the pin B of the IF amplifier, and the signal we see on screen is probed at this point. That's the output of the tuned blue transformer. Right now we have the modulation turned off, and you see the center frequency at 10.7 megahertz. I'm going to turn on the modulation, and we will see the frequency variation around the 10.7 megahertz. And you see the both amplitude and phase vary with the frequency change. And to see this, I set up the generator go in slow mode, so actually its variation of the frequency in 0.5 seconds, so you can see the changing of the phase and magnitude. And I'm going to make a variation in 1 kilohertz, and we probably will hear the sound from the speaker. 1 kilohertz.
This FM antenna with
model on Tennessee, which the committee won't let him forget. I don't see any scenario how Alabama gets in. Maybe there's a smart one here, but they're already 90. Come on, ring those bells like the Christmas. Your chance. Last week you got Oregon State, which is going to be easy. You had your chance.
I just can't say like my father before I
Festival of Holidays y Disney Viva Navidad. Magia es la temporada de fiestas desde ahora hasta el 8 de enero. Participa para tu oportunidad de ganar boletos de un día, un par